Okay, this denial of service attack is really messing us up, but we got this rational function. We want to try to sketch the graph. What we do is find the zeros of the numerator, zeros of the denominator, etc. Okay, I recommend that you write out what you're doing at each step. Write out that the numerator equals x plus 4 times x minus 3. So numerator equals 0 if x plus 4 times x minus 3 equals 0. If you write this logic out, on every problem you do, and there aren't that many of them, you might have to write this out a dozen times. Probably take you 20 seconds each time. That's about 4 minutes of your life. It reinforces this step and says exactly what you're doing in a way that you'll remember. Okay, because right now, people are doing a lot of the right things, but not identifying it, and sometimes then doing the right thing or almost the right thing, but not knowing exactly where it's going to go. Okay, because everybody's made some kind of mistake. Everybody's got a pretty decent start on this. You remember some stuff. You just saw it for the first time last time. So, we're in pretty good shape here. Be better off if you write these steps out. Please let me urge you to do that. Okay. I'm going to keep nagging you about that, so get used to it. All right. So we've got this equation. And how do we solve this equation? This equation splits into the equation x plus 4 equals 0 and the equation x minus 3 equals 0. And the solution to this equation is x equals negative 4. And write the or in here, or x equals 3. So the numerator is 0 if x equals 4 or if x equals 3. Okay. And right there you have a complete statement of what it is that you're doing. Okay. Because some of the most common errors I see people making come down to splitting absolute value equations or applying the zero property of multiplication to solve a problem. We're not seeing those steps explicitly. You'll do much better if we do all these steps. Okay, so, and this is every time I teach pre-calculus, people dive into doing a bunch of calculations without being real clear on why they're doing them. Sometimes that's just because you're not yet real clear on what you're doing. That's why I say write it out and you'll get clear much faster. Okay, so anyhow, there we have it. Zeros are the denominator. It doesn't take long to write this. The denominator is x plus 1. Denominator equals 0. X plus 1 equals 0. So x equals negative 1. It is a one-step solution, so I'm not writing out the details of the solution. So that's it. Denominator is 0 when x equals negative 1. Now the y-intercept when x equals 0, because people are still getting mixed up in this. If you keep writing this out the way I recommend, you're not going to be among those who get confused. And I don't think most of the people here are going to be among the ones who get confused because y'all are doing pretty well. But still, you learn it faster if you do this. So y equals r of 0, which is 0 plus 4 times 0 minus 3 over 0 plus 1. And that occurs then when y equals negative 12. All right, now we've got everything we need to do everything except the end behavior. So let's start sketching our information on a graph. Now, I've recommended that you use vertical dotted lines and label them for the zeros of the function. Okay, so we have a 0 at x equals -4. And a 0 over here at x equals 3. Okay, now what do we have at x equals -1? It's not a 0, because if x equals -1, the denominator is 0, and you can't divide by 0, as I say. If you want to divide this by 0, well, if x is 0, the numerator is -12, the denominator is 0. So start by counting to 12 by zeros and see how far you get. You don't get anywhere. You can't build 12 out of 0, so you can't divide 12 by 0. Of course, you want to divide -12 by something, you take the negative of what you get if you divide the positive number. Okay, so what is x equals -1? That's a vertical intercept. Notice that you have x plus 4 times x minus 3 multiplied by the reciprocal of x plus 1. So this is a vertically stretched reciprocal function. Okay, shifted 1 unit to the left. You know the reciprocal function has asymptotes at the y-axis. If you shift 1 unit to the left, it's going to have an asymptote at x equals -1. And we sketched that in the convention that I'm recommending at x equals -1. And you make that a light solid line so you don't mistake it for a 0. Okay? Now the zeros, the numbers that give you 0, give us the x-intercept. So there's an x-intercept here and an x-intercept here. If you don't have an x-intercept here, the function isn't even defined, because if x equals -1, it's undefined. You have division by 0. Okay, so now you know at this point that you have something that looks like the reciprocal function, but with the asymptote here rather than at the y-axis. Now, depending on whether x plus 4 times x minus 3 is positive or negative at this point, the asymptote could look like this, or it could look like this. Okay. If you flip this thing for a negative sign, it's going to look like this. So it's going to look like one of these things as we approach this vertical line. I don't think that open math explains the reasons for that, but I think you understand it better if you understand the reason. If you understand that, if you just know how to do it, that's going to be okay. If you understand the reason, I think you're going to remember it much better. And you'll have a better understanding of the actual mathematics. So anyhow, there we have it. Now the y-intercept is at -12. So here we have y equals -12. Our y-scale, here's 12 on the y-scale, and here's 3 on the x-scale. 3 or 4 on the x-scale is pretty close to 12 on the y-scale, because when you do functions, polynomials and rational functions, very typically you have to use a completely different scale on the y that you do on the x, because the y values are often huge when the x values are. Okay, so we have the y-intercept, so we can mark that. Okay, so now we have these 3 points in the asymptote here. We've got to go through this point and this point on this side of the asymptote. And we've got to go through this point on the other side of the asymptote. We really need to get the end behavior before we can see what the shape of this graph is. But we know from the fact that we have to go through these points that the asymptote is going to be with the negative x-axis. So we know the asymptote's going to come up like this somehow and turn around to go through this point. But let's figure out what happens before we even get to this point. Let's figure out what's going to happen after we get to this point. So that involves the end behavior. So the end behavior we're going to say if x is large and positive, you have a large positive number here and a large positive number here, divided by a large positive number here. As we saw last time, if x is 1,000,000, as far as we're concerned, 1,004,000 is just about the same as 1,000,000. Or 999,997 is, 1,000,000 minus 3 is still pretty much 1,000,000. 1,000,000 plus 1 is still pretty much 1,000,000. So if you have 1,000,000 times 1,000,000 divided by 1,000,000, what do you get? You get 1,000,000. 1,000,000 divided by 1,000,000 is 1, and you have 1,000,000 here. So if x is a large positive number, why is a large positive number? Just from that reason. And this means the same thing as saying as x goes to infinity, y goes to infinity. If x is large and negative, y is what? Well, if y is negative 1,000,000, you've essentially got negative 1,000,000 times negative 1,000,000 divided by negative 1,000,000. And one of these negative millions divided by this negative 1,000,000 gives you 1. And it still leaves you negative 1,000,000, which is large and negative. In other words, as x goes to negative infinity, y goes to negative infinity. So we can sketch a line like that, or an arrow like this, and kind of, and over here, an arrow like this. The other thing we know is this asymptote is basically, as we get really close to the vertical asymptote, a vertical stretch of the reciprocal x plus 1 function. That's the reciprocal function. And the reciprocal function approaches the asymptote on two different sides. One side approaching infinity, the other side approaching negative infinity. So we know that it's going to be up here like this, down here like this. So right now, we know from the nature of this asymptote that this thing is going to come down here, and then it's going to go negative. Okay, it's go toward negative infinity. The question is, how does it go toward negative infinity? Well, to figure that out, now the rule is when the degree of the numerator is 1 greater than the degree of the denominator, you want to do a long division because you're going to get a slant asymptote. And we see how this works out. We saw it last time, but let's Okay, we can expand this, and I believe we get x squared plus x minus 12 divided by x plus 1. Do the long division. Put a couple little negative signs here to all right, this could form be thing. But coincidentally, both the x squared and the x subtract off and just end up with a negative 12. So we have x minus 12 over x plus 1. So from the long division, r of x equals this is equal to x minus 12 over x plus 1. This means that we can graph y equals x. And somehow, I'm suspecting you got some kind of a mistake here because it really shouldn't. Well, usually you don't get just a y equals x. But since we do, I'm going to accept it. I'm a little uncomfortable with it. I might have made a mistake, but the idea is still going to be the same. So here's the line y equals x. Now, if x is really big, how close is y equals r of x to just plain x? Well, if x is like 1,000,000, this is like 12 divided by 1,000,000, and 12 divided by 1,000,000 is a very small number. So that this is very close to y equals x if x is large. I'll say if the absolute value of x is large. Since large absolute value of x implies small 12 over x plus 1. This gets really small. So the graph gets really close to the graph of x. But what's going to happen here is this graph is going to come out real close to this graph. Now, I'm not sure, in a matter of fact, I'm pretty sure I don't have the wobbles in this curve correct, but it's going to have a negative asymptote at negative vertical asymptote on this side. It's going to go through these points, and then it's going to get close to this line. On the other side, it's going to have a positive vertical asymptote on this side, go through the x-axis here, and it's just going to continue on and get closer and closer to the line y equals x. So that's what your graph is going to look like. Okay, well, that illustrates quite a bit about how we graph rational functions. If you lock that in, then the pre-calculus assignment you're going to have for a week from today, it's going to be a lot easier. Also, I might well put something like that on the test if you know how to do it. There are two advantages. You get that right on the test. It's an optional problem if I put it on the test, so you don't have to do it. And even if you do it and mess it up, it's not going to count unless it helps. Okay, so we have that proviso, but it's to your advantage to get this down as early as possible. Of course, you also want to take time to prepare for the midterm. So you can balance how you do that. Get yourself moving on this. You made a good start, and see if you can get through to the finish on some of these problems. And Open Math gives you a lot of good videos. They use some rules without explaining them. I've given you a little more explanation. Maybe that's to your advantage, maybe it isn't, but I kind of think maybe it will be. All right. No, we're still recording. We don't have a hourglass. So it looks like our BCCS engineers have turned away this latest attempt to nail our firewall. Hopefully they'll continue to be successful. I might have said that too soon. I just hit the button and nothing's happening. Oh no. I don't know if any of that recorded. I also noticed at the end of one of my videos, the voice kept going, but I froze. Which, I don't know. Maybe I'm easier to look at when I'm moving. Maybe I'm easier to look at when I'm standing still. Either way, it's got to be kind of difficult. Okay, well, I don't see anything happening here. This is okay, well, the hourglass went away. There it's back again. I'm going to take a chance and just close this window. It won't even close.
Then wait a few seconds.